So in this class, I will explain in detail about the solution of a stepped bar element. So problem on stepped bar. So this is the stepped bar given. It has got two portions. In the first portion, the cross-sectional area is given as 600 millimeter square. In the second portion, it is given as 400 millimeter square. So taking three nodes like this. First node is here, second node is here, third node is here. This bar is subjected to a force of tensile force of 40 kilonewton in this direction along x direction. Now the question is taking Young's modulus as 200 GPa. So this 200 GPa can also be written as 200 into 10 power 5 MPa, Newton per millimeter square. Determine the nodal displacements. So nodal displacements are Q1, Q2, Q3. These are the nodes. So we have to find out the nodal displacements Q1, Q2, Q3. Then displacement at 1200 mm and 3200 mm from the left end. So this is the left end which is fixed here. So from this left end, at a distance of 1200 means somewhere here it will come, and at a distance of 3200 means somewhere here it will come mm. We have to find out the displacements at these 2 points, and we have to also find the element stresses. So here there are 2 nodes and there are 2 elements. So the elements are 1, 2 and 2, 3. So this is first element, this is second element. It is a one-dimensional bar element, and the nodes connecting 1 and 2, the element 1 connects nodes 1 and 2, element 2 connects nodes 2 and 3. So the question is, we have to find out the displacements at 1, 2, 3. Now, since node 1 is a fixed end, so displacement at that end will be 0. So that is a boundary condition. So Q1 will be 0. This is called as the boundary condition, because at the fixed end, fixed support, you don't have any deflection or displacement. Therefore, the value of Q1 is 0. Only we need to find Q2 and Q3. So this value is 0. That is called as the boundary condition. Geometrical, that is the boundary condition. Now, the procedure is like this. We have to find out the displacement using this equation. Using this equation, which we have studied in matrix and substructures also. Q is equal to K inverse into F. So here Q is the displacement vector, K is the stiffness matrix, global stiffness matrix, F is the global force vector. So you have the relation force is equal to stiffness into displacement. From that you can get the value of displacement. So for that you need to write down the element stiffness matrix of both the elements here. First I will take element 1. For the element 1 we have derived the stiffness matrix of a bar element in the earlier classes, which is given by E into A divided by LE, where LE is the length of the element, A is the cross-sectional area of the element, E is the Young's modulus, 1 minus 1 minus 1 1. So that is the stiffness matrix, element stiffness matrix of a bar element. Now substitute the values for element 1. E value you have to take 200 into 10 power 5 MPa, that is Newton per mm square. Please note that all the units, let us having Newton and millimeters. So stress values you are going to get in Newton per mm square and MPa. Area should be in millimeter square, force should be in newtons. So E is 200 into 10 power 3, A is 600 mm square, he has given irrespective of the section, he has given directly the area. Divide by length of that element, this first element is 2400 mm, that is also he has given, into 1 minus 1 minus 1 1. If you simplify this, you will get 5 into 10 power 4, 1 minus 1 minus 1 1. Now, once you get this stiffness matrix, you have to write here, all of you are very important, this is very important step. So you have to write that this element 1 connects the nodes 1 and 2. Connect the nodes 1 and 2. Therefore, so the first column represents here 1, second column represents 2. Here also first row represents 1, second row represents 2. So these 1, 2, 1, 2, they corresponding to the displacements at that end for that element. For example, in this case there are only one degree of freedom, there is only one displacement at each node. Therefore, it is a 2 cross 2 element. It's a 2 cross 2 element. So 1 2 1 2 we have to write. Similarly, for the element 2, second element, this is the second element. Same expression if you use E is 210 power 3 into area is different here, 400 millimeter square divided by length also is different, 1200 mm into 1 minus 1 minus 1. If you simplify this, you get 5 into 10 power 4, 1 minus 1 minus 1, 1. Please be careful here. This element 2 connects nodes 2 and 3. That is, the displacements are Q2 and Q3, whereas here displacements are Q1 and Q2. So these subscripts you have to write. So it is first column 2, second column 3, first row 2, second row 3, like that. So this is the indication how we have to write the stiffness matrix. Then we have to combine these two elements stiffness matrix to get the global stiffness matrix. So in the global stiffness matrix, all the three will be there. So Q1, Q2, Q3, all the three will be there. So it will be like this. So finally, if you combine these two, since it is common here, 5 into 10 power 4 is common here in both. I can write 5 into 10 power 4 into, now how to write the global stiffness matrix K, I will tell you. You write 1 2 3 here, 1 2 3 here. Now corresponding to this, you have to see both these two. 1 1 common is this 1, that you have to write here. 1 1 common is 1 here. Then 2 1 so common is minus 1, that minus 1 you have to write here. Then 3 1, there is no element which corresponds to 3 1, therefore it is 0. Since it is symmetric, please note that stiffness matrix is symmetric. So once you get the first row elements, first column elements you can write, because in symmetry 1 minus 1 0, in this direction also it is 1 minus 1 0. Next, coming to this 2 2, I have to write 2 2 element here. So 2 2 will be there in both the matrices. You see here 2 2 it is 1 here, 2 2 it is 1 here. Okay, common. So that means 1 plus 1 becomes 2. So you have to add that and you have to write. Then 3 2 is minus 1. So that you have to write. So since it is symmetric, once again, second row and second column they are same. So this becomes minus 1. And last element will be 3 3 is 1. So that I have written here. So this is how you can combine the element stiffness matrix to get the global stiffness matrix. The corresponding global force vector. So we need three things. One is the stiffness matrix, second one is force vector, and third one is displacement vector. We call it as vector because it has got only one column. So for the global force vector, you have to observe the diagram. In the given problem, he has not given any load at node 1. So therefore it is 0 at node 1, and that means in the direction of Q1, he has not given any load, therefore it is 0. In the direction of Q2 also, he has not given any load, therefore that is also 0. But in the direction of Q3, see here, Q3, in the direction of Q3, he has given a force of 40 kilonewton. So this should be converted to Newton. Be careful here. Newton, therefore it is 40,000. So first value corresponds to the force in Q1 direction, which is 0. Second value corresponds to force in Q2 direction, which is also 0. Third value corresponds to force in Q3 direction, which is 40,000 Newton. We have to convert it to Newton. That is F. Then the nodal displacements vector is Q1, Q2, Q3. So that is the unknown vector here. This we have to find out. Out of these three, you know that Q1 is 0 because it is fixed at node 1. So at the fixed support or at the fixed end, you don't have any displacement. Therefore, because it will be having this Q1 will be 0, Q1, Q2, Q3 will be there. Now, what we have to do here is we have to eliminate. The using the boundary conditions certain rows and columns. Now, first we will find out the nodal displacements. To find the nodal displacements, the formula is K into Q is equal to F. K into Q is equal to F. or Q is equal to, if you bring this K to that side, it becomes K inverse into F. Now K inverse means you know the value of K, you know the stiffness matrix K here. Inverse of this we have to take, but you have to eliminate the row and column where the value where the displacement in which direction the displacement is 0. For example, in this case Q1 is 0. Since Q1 is 0, this first row and first column they are eliminated. So first row and first column correspond to Q1. Please note that. So this and this are eliminated. So only you will be left with 2 minus 1 minus 1 1. So we have to take the inverse of that 2 minus 1 minus 1 1. I have written here inverse of that. But here inverse of 5 into 10 power 4 is reciprocal of that. So 1 divided by 5 into 10 power 4 into inverse of this into in this F also we have to eliminate this first one. 0 is not there because Q1 is 0. That value will not come. Only second and third will come here. So that means we are writing for Q2 Q3 Q2 Q3 like that. Now you know how to find the inverse of a second order matrix. It is very easy. So inverse of a second order matrix is nothing but the adjoint of this matrix divided by the determinant of that matrix. So adjoint is given by all of you observe here. For a second order matrix, adjoint is nothing but you have to interchange the principal diagonal elements. That means if the matrix is having 2 1 here, you have to write 1 2. Interchange the principal diagonal elements and change the signs of the secondary diagonal element. This is secondary diagonal element. So minus 1 is there here. You have to make it plus 1. That's all. It's very easy to write the inverse of a second order matrix. So here, once again I will repeat. So you have to interchange the principal diagonal elements. That means 2 1 becomes 1 2. Change the signs of the secondary diagonal element. So magnitude wise it will be same, but you have to change the sign. So minus 1 becomes plus 1 here, minus 1 becomes plus 1 here. Suppose if it is 1 1 here, then this becomes minus 1 like this. Okay? So that is they divided by determinant. So determinant of second order matrix is product of the principal diagonal elements minus product of the secondary diagonal elements. So product of principal diagonal elements is 2 into 1, that is 2, minus product of secondary diagonal element minus 1 into minus 1 is plus 1. So it becomes 2 minus 1, which is 1 itself. So this is the inverse of this matrix. Inverse means if you multiply a matrix by its inverse, you are going to get a unit matrix. So A into A inverse is equal to I. That is the concept of matrix algebra. So this is the concept. So when you multiply a inverse of a matrix by a matrix itself, you are going to get the product as unit matrix. Now once you get this inverse, now you have to multiply that by this force vector. So you know how to multiply the matrix. So here if you multiply these two matrices, 1 into 0 plus 1 into 40,000, then second element will be 1 into 0 plus 2 into 40,000, and once again that should be divided by 5 into 10 power 4. So you are going to get the value Q2 Q3 value. The first value what you get is Q2, the second value what you get is Q3. So in this problem you have got the nodal displacement at second node Q2 value as 0.8 millimeter. So the answer is in millimeter, and the nodal displacement at the third node Q3 as 1.6 millimeter. You can check the answers. So since the answers are positive, your assumed direction of displacement is correct. So that means Q2 will be in this direction only, Q3 will be in this direction. That means it elongates. The ball elongates in this direction. Natural, because the tension force is acting in this direction. So therefore elongation also takes place in this direction. Suppose in any problem if you get negative value for the displacement, the displacement is in the opposite direction. Suppose if you get Q2 as minus 0.8, then the displacement will be in this direction. That can happen if they give a force here also. Okay, so that force we have to take here. Once again, for writing the force also, you have to take here I have taken 40,000 positive because this force 40 kN force is acting in the same direction as that of Q3. Please note here. Suppose if they give 40 kN in the opposite direction, so this 40,000 we have to take it as negative. So please note that when you are writing the matrices, force matrix, when you are writing for force vector, so if the force is given in the direction of the assumed displacement, then it is positive. If the force is in the opposite direction, then it is negative. So this is how we can find out the nodal displacements Q2, Q3. So now Q1 is 0 as per the boundary condition. Q2 we got 0.8 mm. Q3 we got 1.6 mm acting in the direction of the force. That is the first part of the problem. Nodal displacements over. Second part, displacement at 1200 mm and 3200 mm from the left hand support. So for this we have to use the shape function concept. So a shape function or interpolation function is the function which is used to find the displacement or deformation of at any point by knowing the nodal deformation or nodal displacement. So you have the concept here, u is equal to n into q. This I have explained in the earlier lectures. So u is the displacement required at any point within the element, n is the shape function, and q is the nodal displacement. Now here n consists of two shape functions here because it is a two node element, bar element n1, n2. And you know we have derived that n1 is 1 minus zeta by 2 and n2 is 1 plus zeta by 2. So those two things you have to remember for a two node bar element in natural coordinates. The shape functions are 1 minus zeta by 2, 1 plus zeta by 2, where zeta is the natural coordinate in the x direction. Yes. Now here, let us go to the second part now. U is equal to n into q. So already we got the value of q. So n1, n2 if you find out and if you substitute and multiply, you are going to get the value of u. Now n1, as I already told, it is 1 minus zeta by 2. This is the shape function n1 for a two node bar element. n2 is 1 plus zeta by 2. This is the shape function for a two node bar element n2, right? So n1, n2 they are the two shape functions. Now how to get this zeta? So once you get the value of zeta, then you can get the value of n1 and n2. So zeta is defined like this. This is very important. You have to remember this. Zeta is the relationship between natural coordinate and global coordinate is zeta is equal to 2x minus of x1 plus x2 divided by LE. You have to remember this. So here, first what I will do here is, now at what point he has asked? He has asked the displacement at 1200 mm first. So from this left support, this is left support. So from this you take point A at 1200 mm. So that is x distance is 1200. X1 is this value. So what we have to do here is, this is the element now. 1, 2 is the element. In this 1, 2, this is the first element. In this, point A is here. Point A is here. So this is the value of x1. x1 is 0 because x is measured from this end. Here x1 is 0. The value of x2 is this value, that is how much? 2400. 2400 mm is x2, 0 is x1, and x is this value. So at what point you need the displacement, that is x, that is 1200. Now if you substitute that 2 into, so zeta at A will be, what is the value of zeta at A? It is 2 into 1200 is x, minus of x1 is 0, x2 is 2400, divided by LE is length of element 2400. If you simplify this, you will get 0 itself. 2400 minus 2400 becomes 0 numerator. Therefore, zeta becomes 0 at A. Zeta value is 0 at A. Naturally, because if you observe the earlier video, in a two node bar element, left hand zeta will be left hand node, zeta will be minus 1, right hand node, zeta will be plus 1. Of course, here A is the midpoint because total is 2400, midpoint is 1200, naturally zeta will be 0. Anyway, at other point, any other point if they ask, so that corresponding value of x you have to take here. So now in this case zeta has become 0, therefore n1 is 1 minus 0 by 2, which is 0.5, and n2 is also 1 plus 0 by 2, that is also 0.5. So these are the values of n1 and n2 at point A. Very important. That n1 and n2 value varies from point to point. So therefore now I have found out u at A as n1, n2, q1, q2 you have to take. Why we have to take q1, q2 is we are writing the first element. In the first element that point lies. This point A lies in the first element. Therefore the nodal displacement vector consists of only q1 and q2. So those two I have to write here. Now substitute the values. n1 is 0.5, n2 is 0.5, q1 is 0 by the boundary condition, q2 is 0.8 mm we have got here. Now multiply these two. Multiply these two matrices. The 0.5 into 0 plus 0.5 into 0.8 which becomes 0.4 mm. So 0.4 mm is the displacement at the point A, that is at a distance of 1200 mm from the left support. Similarly, at the point B, now he has asked at one more point, that is 3200 mm. So 3200 mm means from this is the origin now. This itself is the origin, x is minor from that end, this came only. Now here, up to this it is 2400. So x1 becomes 2400. Now this becomes x1, this becomes x2 because this is the second element. So the second point is B point is here, it lies in the second element. So x1 will be now 2400, x2 will be now 2400 plus 1400, 3600. Please note here, x1 is 2400, x2 is 3600 and x is 3200. So from this end, so this B is at a distance of 3200. Now share the equation. If you use 2x minus of x1 plus x2 divided by LE, length of the element in the for the second element is 1200. Please note this length of the element is 1200 here. So 2 into x is 3200 minus of 2400 plus 3600, this is x1 and x2 divided by 1200. This is for the second element. So if you simplify this, you will get 0.33. That means the value of zeta. The value of zeta at point B is 0.33. Now substitute that value of zeta and get the value of n1. So n1 once again it is 1 minus zeta by 2, which is 1 minus 0.33 by 2, which is 0.33 itself, and n2 is 1 plus zeta by 2, that is 1 plus 0.33 by 2, which is 0.67 or 0.66. So that is it. They are the values of n1 and n2. Once again, if you want displacement u at the point B, use the formula n into q. So here be careful, n1, n2, these values you have to take 0.33, 0.67 because it lies in the second element. So displacement vector will be q2, q3. Please note the difference here. Here it is q1, q2 because the point A lies in the first element. You have to take q1, q2 as the nodal displacement. In the second case, since the point B lies in the second element, we have to take the nodal displacements as q2, q3. So q2, q3 we have to take. Now we have got the values of q2, q3 as 0.8 and 1.6. Once again you multiply these two. So the value will be now 0.33 into 0.8 plus 0.67 into 1.6, which comes out to be 1.336 millimeter. So here the displacement here is, this value is 1.336 mm and this value is 0.4 mm. So that is about the displacement at the 2 points A and B. So displacements at any required point can be obtained by the expression n into q, where n is the respective shape function. Since it is in this case a two-noded bar element, only two shape functions will be there, n1 and n2, and depending on which element that point lies, we have to take the displacement matrix. Now the third last one, he has asked us stresses, element stresses. So we have the formula for finding stress in a bar element. So we have given, I have derived it. So sigma is the stress, sigma is equal to E into epsilon. This is the general equation by Hooke's law. stress is equal to Young's modulus into strain. Epsilon is the strain, and of course this epsilon is once again can written as B into Q. B into Q. So where B is the strain displacement matrix. So I have derived in the earlier class about that strain displacement matrix. So strain displacement matrix for a ball element B is equal to, this is equal to 1 by LE minus 1 1. So this is the strain displacement matrix for a ball element. Now if you substitute these things there, you are going to get sigma is equal to E into E is constant here, Young's modulus. B is 1 by LE into minus 1 1 into Q. Now we will calculate the value of sigma for both the elements. For element 1, the stress in element 1, so that is in this it connects 1 and 2, node 1 and 2, it connects node 1 and 2, this is element 1. In this the stress is sigma 1. So sigma 1 is equal to, I will write E into 1 by LE of that. LE of the first element is, length of the element is 2400 mm. So 2400 mm. And E also you can substitute. So it is, the E value is 200 into 10 power 3. Okay, it is given here 200 into 10 power 3. 200 into 10 power 3 is the E value. Then into 1 divided by 2400 into minus 1 1 into Q, we have to take Q1 Q. Please note here, because we are finding the stress in the first element, we have to take the nodal displacements in the first element. So now this Q1 is 0, of course, you know that. Now if you simplify this, so this becomes 200 into 10 power 3 divided by 2400, okay, into minus 1 1. Q1 is 0 here, Q2 is 0.8. Okay, so these are the if you simplify this, you are going to get the value of sigma 1. I think you will be getting 66 Newton per mm square, maybe the answer. Please check it, Newton per mm square or MPa. So that is the stress in the first element. Of course, it is tensile stress because you can see that the ball is subjected to tensile force. Now coming to element 2, on similar lines, you can find out the stress in element 2 by using the same expression where the LE value is 1200. For the second element, length of the second element is 1200. Therefore, for element 2, I will write here, for element 2, sigma 2 I will take. This is element 2 which connects nodes 2 and 3. This is element 2. The stress in this is sigma 2. Sigma 2 is equal to 1, E is once again 200 into 10 power 3. 200 into 10 power 3 divided by LE is 1200 mm for the second element into minus 1 1 into Q2 Q3. Please note that. Note the difference here. For the first element, you have to take Q vector as Q1 Q2 because we are finding stress in the first element. For the second element, since the nodal displacements corresponding to second element are Q2 and Q3. So this is the second element, Q2 Q3. Now substitute the value of Q2 as 0.8, Q3 as 1.6, and once again multiply this matrix like this. So you have to multiply minus 1 into 0.8 plus 1 into 1.6 into 200 into 10 power 3 divided by 1200. If you do that, you are going to get the stress in the second element as 100 MPa. Please check it out. So 100 MPa. Once again, this is also tensile. We have got positive value. So and the direction of stress is also tensile. So this is the stress value in the second element, 100 MPa. This is the stress value in the first element. So this is a complete problem which may carry 20 marks in the examination. So two stepped bar problem. First, we have found out the nodal displacements. There are 3 nodal displacements, out of which one nodal displacement is 0 because it is fixed end, there is no displacement there, only unknowns are Q2, Q3. So we have written the stiffness matrix of both these two elements separately, element stiffness matrix, then we have combined it to get the global stiffness matrix, then we have eliminated the terms which where the or at which the nodal displacement is 0. We have condensed it, so static condensation technique we call it as. So that we have done. So then what happens at global stiffness matrix, third order matrix, it has reduced it to second order matrix. Then what we have done is using the equation F is equal to K into delta or K into Q. So we have found out Q is equal to K inverse into F. So by writing the global force vector and global stiffness matrix, we have found out the displacement vector, the nodal displacement vector. Then afterwards, he has asked the displacement at some point within the element. For that, we have found out the shape function at the required element n1 and n2 using the concept 1 minus zeta by 2 is n1 and 1 plus zeta by 2 is n2. After finding zeta, we have got n1 and n2. Then using the equation u is equal to n into q, we have found out the displacement at the required point. Then he has asked the stress value. So to get the stress value directly, we have used the Hooke's law, wherein we have used the strain displacement matrix. So this B is the strain displacement matrix for a bar element. So since it's a stepped bar problem, so strain displacement matrix for a bar element is given by 1 by LE into minus 1 1. So that we have used and we have found out the stresses in the element, in both the elements.